Hi, in this video, we want to take a look at evaluating our supervised learning models after we built them. All right, so our goal is to understand, do I have a good model? Do I have a bad model? Is it good enough for my project? All right, and so we want like evidence. We want some kind of form of evaluation to decide if I have a good model. Now, something to consider is when I say good, what does that mean? Think about evaluating if someone is athletic. Okay, so how could somebody be athletic? Well, they could be like we could measure that by their bench press, or maybe we can measure it by how fast they can run a 5K, how fast they can run the 40-yard dash, how fast they can run a marathon. We'd also go by their speed when they're riding a bicycle. We could go by their flexibility, but we could also use body composition. There's a whole bunch of different ways to measure athleticism. All right, but you're going to reach different conclusions depending on how you measure. And so one thing that we need to do, we need to understand the measurements so that we better understand what we're evaluating when we are trying to decide if our model is good enough. All right, so and something I want to say is I want to emphasize model quality over all other aspects, over the technical aspects of building a model. It's more important for us to make a model that's reliable and we want a reliable, trustworthy model far more than we want something that is sexy and exciting. And so if I want good quality modeling, most of the time I need good quality data. Garbage in, garbage out. Put that in reverse. If I put good quality data in, I have the opportunity to make a good model, as long as I don't do something stupid. The models that I'm going to talk about in future videos will most of the time be models that are trustworthy for building down the road. All right, so we want to understand how robust and how accurate our predictions are going to be if we use a particular model. Something that's kind of surprising is that accuracy alone isn't enough. Why isn't accuracy enough? Consider a situation I have like fraud data set. Let's say 1% of some transactions are fraudulent. That's really, really high, but just for the sake of argument, for the numbers, let's keep it simple. Let's say 1% in my data set are fraudulent, 99% are not fraudulent. Well, bank comes to me, Aaron, go and build a model, and I want it to be very, very accurate. All right, well, you know what I can do? I can write some code that says not fraudulent, and I'll be accurate 99% of the time, and I don't do any work. I just say not fraudulent to every single one, and boom, right off the bat, I'm 99% accurate. Huh. Well, but I'd be missing something, right? I'd be missing that whole 1%. I'd be missing the whole point of the model. So accuracy isn't enough. Even though I was 99% accurate, that's not going to be sufficient for employment. So what we want to do is we want to pull in other measurements that take into consideration that imbalanced data aspect that we have. All right, so in this video, we're going to use the Kaggle's mushroom classification data sets. Here's the website for it. Now, in a previous video, I went through and I did data prep. If you remember the data prep I did, the big aspect from that is that for the categorical data, I attempted to do binary binning. So my categorical and ordinal variables were binned into 2 levels every single time. Now, that is very severe binning, very extreme binning. I can't bend anymore and have a meaningful column. I like that because I only have one dummy variable to work with in the situation. And this is a good technique for first go around as I'm exploring options to work through. What I do at work in real life, I start with that dummy variable presentation. And then when I identify which predictor variables are super important and model structure that I want to use, then I go back and I tinker and loosen up the binning to get a more refined picture of what's going on. But I do that after I have an idea of which variables are on like my long list to try. When I work on my variable selection, I tend to start with like a long list of variables, and then I kind of like whittle it down, then I whittle it down a little bit more, and then when I get to the nitty-gritty, that's when I really start digging into my variables and reevaluating my data prep before I actually build my model for production. All right, so the first thing I'm going to do in this example is I'm going to prepare my workspace. So I'm going to tell R to not give me too many digits when it prints stuff out. The larger this number is, the more R will try to avoid scientific notation. Sometimes it just has to do it. There's no two ways about it. And this -1 warning is to suppress warning messages. So I tend to mix it and match standard evaluation and non-standard evaluation in R. Tidyverse uses non-standard evaluation, but there's some things that programmatically are just easier to program if I kind of go across the tidyverse way and the classic R way. And so I'm using whatever's easiest in the moment for programming, but the tidyverse will start spitting out some warnings at me. I say, hey, just skip those. I'm clearing my workspace to make sure I don't have any artifacts that will interfere with what's going on. And the McGritter package is to pull in the piping operator. All right, I've already built up my prepared data sets. I'm using readr because readr is a pretty fast package for loading. It's not the fastest. Data.table is faster, but it has its own special like syntax, and I prefer to just use more of a classic R approach, just because it's consistent. By specifying the column types, I can greatly speed up the loading because readr doesn't have to go down the column and figure out what each column is. Now, the data set I have is, I don't have a train test column. So I'm going to go ahead and create that. And I'm using random number generator. So that's random uniform 01 standard uniform. If it's greater than 0.5, it's part of the training set. If it's less than or equal to 0.5, it's part of the test set. And I can change this parameter as I wish. I tend to put less in my training data initially as I'm building my model because I want things to be fast, especially when I'm initially building things, to do things like quick. So I sacrifice my training data to put more into test sets, and I've got less data to work with when I'm training, but my models are faster, my computations are faster, and I find that that's a better way for those initial runs to figure things out. Now I'm going to build a logistic regression model. So I'm using the generalized linear model function. It's a binomial distribution. The default link functions is the logit function. I could change it to others such as probit, but honestly, logit is very flexible, and it's flexible enough that usually if like probit, it would be the best way. Logit isn't too far behind. And so if I don't have a theoretical reason for it, or a stakeholder doesn't want me to use probit, I just stick with the logit like function. All right, so I chose to use population, gill color, and bruises as the only predictors. And so you'll notice this is only 3 predictor variables in there. And I'm using 2-way and 3-way interaction in here by doing the star multiplication in there. And I'm using my data set, and I'm filtering so that it's only the training data. All right, so now after this has built the model that I'm going to use for the examples, I need to make predictions. All right, so I'm going to use the predict function. I want the response. So with a generalized linear model, predict has 3 options. We have the length function value, which would be the log odds for this particular model, or the probabilities, which is response, or we can get like the terms out of there. I've never had a reason to work with the terms, but it's an option for us. So if I leave it on default, it's going to give us the link function value. So it'd be log odds for a logistic regression. If I want the probability, I need the response. And then to get the classification, edible or not edible, for this case, 1 is edible, 0 is poisonous. I'm going to just round it. All right, so here, something that I'm doing is I'm saying that with a probability of 0.5 or higher, so if my model probability is 0.5 or above, excuse me, it has to be greater than 0.5, I'm going to say it is edible. If the probability is less than 0.5, then it's going to round to 0. I'm going to say that is poisonous. Now, if I think about that for a moment, is a model probability of 0.51. If your model said it's the probability of it being edible is 0.51, would you take that bet on eating that mushroom? Would you want to risk it? That's pretty close to being poisonous. So one thing that we could do, I'm not doing it here, but we could raise that threshold. So instead of here having a 0.5 requirement, I could set it up so that the predicted probability, let's say if it's 0.9 or above, then we're going to put the class at 1. If it's less than or equal to 0.9, I could put it at 0, something like that. And so here I would just use a logical vector to do that, like predict probability greater than 0.9, and then as numeric to convert it to a 0, 1 value. All right, so what I'm going to do right out the gate is I'm going to spit out a whole bunch of statistics about my model. And the reason why I'm doing this is because this function gives us a whole bunch, and this is a good place to go. This is probably one of the most important things to walk away from this video with is this function right here. And so what I'm going to do is I'm going to take the predicted classification that I have. It needs to be a factor. I'm going to take the true values, which also needs to be in a factor, and then I put it into the confusion matrix function from caret, and it's going to spit out a bunch of statistics about my model to let me know, do I have a good model, and I can make a judgment. Now, there are several things that we can put in there. If I give a mode of everything, it gives all the options for me. So I'll just put down everything, and we'll look into these next. Now, after we look at these statistics, I'll start explaining the ones that are most common and the ones I feel that are most important as we work through. All right, so first and foremost, I get a confusion matrix right here. All right, so what's going on? I've got 0, 1. Here are the values of my model's predicted poisonous or edible. 0 is poisonous, 1 is edible. And here's the actual true value. So here, my model correctly classified the mushroom as poisonous when it was. Here, my model correctly classified the mushroom as edible. Now here, 310 times the mushroom was poisonous, but my model said it wasn't. So my model, sorry, I got that backwards. 310 times the mushroom was edible, but my model said it was poisonous. 397 times the model was poisonous, the mushroom was poisonous, but my model said it was edible. All right, so let's think about that for a moment. Like that's proportionally, my model is detecting difference. We've got the majority in here are correct, but if you were the one eating those mushrooms, do you trust this situation? Are you willing to take that risk? All right, so what we could do is raise that instead of 0.5, go 0.8, 0.9 required probability to declare it as as being edible. Now, when I do that, well, what's going to happen? Well, if I raise the criteria for my model declaring that it's edible, then there are going to be times when it's edible, it's truly edible, but my model makes a mistake and says that's poisonous. So there's a repercussion there too. So if I was out in the woods and foraging and I needed to survive off of this model, well, then I would be going hungrier than I needed to be, but I would be exposing myself to less risk of being poisoned. So there's two penalties here. Just like in hypothesis testing, we have a type 1 error, type 2 error, and here we we can balance that by setting the cutoffs depending on what the penalty of the error is. Overall, we have a 0.83 accuracy. Here is the confidence interval for the accuracy. And here's our no information rate. I don't usually use that. Here's a p-value for accuracy being greater than the no information rate. So we reject the null hypothesis and go with the alternative. Remember that the alternative always has an equal sign. Sorry, the null always has an equal sign. So here we reject the null in favor of the alternative. We conclude that accuracy is greater than the no information rate. Here is the kappa statistic. And next we have our sensitivity. We'll talk about that in a little bit. Our specificity, our positive predicted value, negative predicted value, precision, recall, F1, prevalence, detection rate, detection prevalence, and then balanced accuracy. All right, so sensitivity and specificity we'll talk about, precision, recall, and F1 we'll talk about, and balanced accuracy, I feel like that's pretty intuitive, that this is accuracy considering the balance of those zeros and ones that I'm putting in for edible and poisonous. And so if I was in that fraudulent situation where I had only 1% was fraudulent, that's a very imbalanced data set. And so standard accuracy is not the way to go off of that. So this balanced accuracy, if I have an unbalanced data set, I don't want to use this accuracy. I want to use this one as the way of measuring. The data here is pretty balanced. It's not perfect, but it's pretty good. So, I'll go ahead and just use accuracy as is. Now, when I did this, this was on the test set. You'll notice that when I compute these statistics, I'm computing training statistics and test statistics. And remember, I split my data in half. So something that's kind of funny, kind of surprising about this is that my training statistics on this model are actually slightly worse than my test statistic. All right, so the vast majority of time, you will see that your training statistics are better than your validation statistics, which are better than your test statistics, which are better than the statistics from actually launching your model in production. Expect it to be that way. If it's severely not that way, there's probably an outlier, like some anomalies floating around your data that you need to fix. So when you go through, if you see your training is worse than your validation, or validation is worse than test, then you probably have an outlier in the data set. Go and find it, fix it, do something about it. All right, so in general, the more flexible my model is, the more complicated my model is, the more of a difference in the statistics I will see, because there's just differences in the data. So the model was built on the training data. So it was fitted, it was tuned to the training data. And so the model is going to look like the training data. And so most of the time it's going to be better than validation, better than test, better than score data. Now, when you have a simpler model structure like we do here, it's logistic regression with only 3 predictor variables. It does have interaction, but it's only 3 main effects going into there. It's a pretty simple model. Usually when I have simple linear regression models, or when I say simple, I don't mean simple multiple linear regression models, and I have relatively simple logistic regression models, what you see is what you get. This is a huge advantage of these models over like stochastic gradient boosting, random forest, k-nearest neighbors, neural networks, because they're so simple that what I look at and what I build up initially tends to be what I get down the road. And this is an indication that I can trust this model pretty well, that I'm not overfitting. And so we can run through, we see that the statistics overall, if you pick through bit by bit by bit, are slightly worse than the ones we looked at when we looked at the test set version. How I got this was you'll notice that here I split my data into training and the test data, and then I broke up the data into two groups, then I dropped the two groups into the confusion matrix function. And that's how I got this with a for loop. All right, so accuracy. Accuracy is the one that's easiest to explain to our stakeholders. It's the simplest one, like fraction of times, how often did you get it right? It's as simple as that. Take the number of times that you got right when you called positive, number of times that you got it right calling negative or zeros and ones, and then divide by the total number of opportunities to make a call. And that's it. So what percentage of the time did you make the right call on the classification? Now, sensitivity, and also called recall, what this measures the proportion of actual positives that were correctly identified. And so here, this is particularly useful when false negatives are costly. All right, so what we're going to do, we're going to take our true positives. And so in this naming convention, we have true positive, true negative, false positive, false negative. So if it's a false, our model made a mistake. And if it's a true, our model made the right call. And then we have positive or negative, depending on if we made which way we went. Okay, so the sensitivity and recall is number of true positives divided by the number of true positives plus the number of false negatives. All right, so here, this is going to end up being, this denominator is all the times in the data set that it was truly positive. And so like every single time it was a truly edible mushroom in the true correct target variable column. And this is the number of times that my model got that right, but only for like the edible case. Now the specificity, here we're going to take the true negatives divided by true negatives plus false positives. So here it's supposed to be a negative, but my model made the wrong call. And so we take the number of times that we got right calling negative, and all the times in the data, the target variable is negative. And so here, this is the number, the count of the number of mushrooms that truly are poisonous. Of those, how many times did my model get it right? All right. And then precision is the number of true positives divided by true positives plus false positives. So this is all the times that the model called out positive, correct or incorrect, is the denominator, and the numerator is the number of true positives. And so this is a crucial when the cost of false positive is high, like spam detection. And the confusion matrix was that 2x2 table we looked at a little bit ago of letting us know, like, how is our model performing? On the diagonal, in terms of like a matrix, that's where we want to see our values. We want, ideally, if we had a perfect model, we would have 0 off the diagonal, and all of our numbers would be along that diagonal there. Now, the F1 score, what this one does, this works to balance precision and sensitivity. So remember, here's our precision. So true positive divided by true positive plus false positive. And sensitivity is true positive and true positive plus false negative. And so it's possible to have one of these really high and sacrifice the other one. So we can sacrifice precision to raise sensitivity. We can sacrifice sensitivity and sacrifice precision by shifting up and down our criteria for calling edible. So if I raise the criteria for being edible, I'm going to reduce how frequently I get a false positive, but I'm going to increase the number of false negatives. And so there's a balancing act of, there's a penalty for calling something poisonous when it's not. There's a penalty for calling something edible when it's not. Calling it edible when it's not is far worse, but we want to balance those two. And so as I adjust the criteria, the F1 score tries to consider both sides simultaneously for us, so that we can, we can make a judgment call on what's best. These decisions are more important when I have unbalanced data. When it's 50-50 on the levels, which is close to what we have here, then it's like what the cutoffs are, like that, 0.5 is, it's not such a, it's not so hard to wade through this. But when I get imbalanced data, I have to really, really consider what is the right cutoff for this. And these metrics help us decide those cutoffs. All right, now area under the curve. All right, so I'm going to scroll down. We're going to look at the ROC curve for a moment. Okay, so what we're going to do, this color bar represents the value of the cutoff that I'm setting up. Now, probabilities can't go up to, they can't go above 1, but it's, an automated system, it's a computer. It went slightly over 1, and here we want to go all the way down to 0. Well, what's going on here is that I'm saying at this point, if it needs to be exactly 1 model probability of being edible for me to say edible. Over here, it has to be any probability greater than 0 is called edible. And then along here, I'm changing the model probability cutoff for that. So like, here, we're saying it has to be at least one for the model probability. Over here, like the cutoff, let's say, is something like 0.9. I have to have at least a 0.9 model probability. Over here, we need at least a 0.7 cutoff. Over here, we need at least let's say 0.6. We need at least a 0.5. Here we need at least a 0.4. Here we need at least a 0.2. Here we need like at least a 0.1. And you can see it's going along the values there. And now, for each of those values, as I change the cutoff for declaring edible or poisonous, that's going to change my rate of true positive values, and that's going to change my rate of false positives. Okay, so if you don't want to ever have a false positive, the way to protect yourself from that is to never declare it as positive. All right, so that would be, in this situation, if I'm truly, truly, truly scared of making the wrong call on the positive case, well, I could just say a mushroom is never edible, never, ever. And I will never make a mistake of a false positive. Now, kind of kills the point of data science, so we're not going to go that route. But if I just say, hey, there is no such thing as an edible mushroom, every single mushroom is not edible, then I'm down here, super, super low at the very end of this, and I'm completely protecting myself from false positives. Now, as I admit, as I become less stringent, let's say that I need to have at least a 0.9. If it's a 0.9 model probability of being edible, then okay, I have a true positive rate where I'm getting it right, but I also have a false positive rate. Now that I'm letting some opportunity for a mushroom to be declared edible, I've also just introduced the risk of making a mistake on this front. And so now it's relatively small, but it is there. And as I adjust, you'll notice that as I loosen the criteria for being called edible, you'll notice that my true positive rate goes up, but also my false positive rate goes up. Loosen it a little bit more, true positive rate goes up, false positive rate goes up also. And it keeps on going in this pattern. And you can see that we hit diminishing returns. Okay, so how we want to use this is that we can use this to help identify where is a good cutoff. So there's a couple of different ways to adjust this. One way is to say, hey, what point is closest to this corner right here? This corner is the 0, 1 coordinate. And if we go by the Euclidean distance, some people like to choose the point that's closest to here along the ROC curve. And so maybe about here, let's say, and that would be, we would be, gosh, maybe, let's say this is just 0.7. So if I said 0.7 was high enough to declare edible, then I would have a false positive rate of 0.2, but my true positive rate would be 0.8. All right, and so I'm balancing that. Another criteria for selecting optimal would be to say that, hey, I want to go with the sum that gives me the highest true positive plus 1 minus the false positive. I take true positive plus 1 minus false positive. Where along this curve gives me the largest value? Neither one of these are perfect. Frankly, you need to talk to your stakeholders and your boss and the people involved in the project to make a decision on what is best. So now, for my model overall, as I look at this, so I built the model and I want to know, is this a good model? Is this detecting things? Well, if I had a perfect model, if I had the best model on the planet, what would happen is that this line would be going straight up to here, and then it would go over like that. And so if I had absolutely the best model possible, then the entire area underneath that curve would be 1. 1 times 1 gives me an area of 1. All right. Now, so the area under the curve gives me a measurement of how well I can adjust the criteria for calling edible or poisonous and get coherent results. And so area under the curve is like a global overall measurement of how well my model is going to be if I want to be able to adjust the cutoffs overall. Now, a area under the curve of 0.5, that corresponds to, if I was to take, let's say the model gave me the ROC curve of a straight line going from 0, 0 to 1, 1. If I did a straight line from 0, 0 to 1, 1, then I would have a straight line linear equation, just like you did in middle school, or actually for that one, that's probably elementary school. Straight line, and the area under the curve would be that triangle. Well, here, base times height, base is 1, height is 1. Base times height divided by 2 is 1/2. So if I see an area under the curve equal to 1/2, that means that my model overall is just like random guessing. And so that means I would not have a very good model. If I see an area under the curve of less than 0.5, then my model overall globally, in terms of the cutoffs, is actually performing worse than random guessing. And so in that case, I probably don't have a very good model. And so like here, this is for test and this is for training. And if you look at the two curves really, really closely, you'll notice that once again, the test curve is a little bit better than the training one. I'm really surprised by that. All right, so area under the curve is the total area underneath that curve. It ideally perfect model would have an area of the curve under 1. Random guessing will be an area under the curve of 0.5. Less than 0.5, we have worse than random guessing. So when I say random guessing, in that situation, let's say my original data set, I had 0.25 are edible, 0.75 are poisonous. If I did a random number generator to declare edible 0.25 per time, fraction of the time, and 75% declare poisonous, if I just did a random number generation like that, we would get an area under the curve of area under the curve of 0.5. If I see 0, 0 is the worst value possible, my model is doing worse than random guessing, which is possible. And I have seen models do that. That model did not make it to production. All right, and here's the area under the curve of 0.89, area under the curve of 0.9. Then you notice that once again, the test one is actually better than the training one. Kind of surprising. Here, they're close enough that I'm not too worried about it. If there was more of a gap, I would start digging in, looking for outliers or some anomalies or something weird going on in my data. Usually the one that has the lower values will have an outlier. That's a way for you to detect outliers, like while you're doing your process, while you're working on your modeling. All right, now this function here, the prediction function from the ROCR package, this has a lot of utility, a ton of utility, and a bunch of other statistics for your model that I'm not going to talk about, but I want you to know about them, so I'm going to present them here. And so all of these here, here we have our accuracy, our area under the curve. This is also a modified version of area under the curve. We have our chi-squared, here, false negative rate, false positive rate. We have our lift. We've got our odds. Root mean square error. We have our sensitivity, specificity, true negative rate, true positive rate. We have all of these statistics that this function will give us if we want them to. And so something that's really nice about this package is that by just using one package, I can get a whole bunch of different statistics out for me. Here I only used it for area under the curve, but there's a lot of utility. If your stakeholders, your boss, or someone wants a particular metric, it's probably in this list. Now, extracting the value is kind of cumbersome. Here, just you use a performance function to get it out. It's been a while since I've done this, and I need to look up how to perform this. But it will give you a lot of utility. There are other functions that will give you the AUC actually easier and simpler, but this package is more useful because it does a lot of nice graphs for us, and we can get a wider range of statistics to come out. Now we can also use Kaiki's information criterion and a Bayesian information criterion. So here we're taking into consideration how well the model is fitting with the log likelihood aspect of the calculation and the penalty term for complexity. And so AIC and BIC are good at telling us, compared to other models, which one is the best of several models, when we simultaneously consider model performance and we consider complexity of the model. And the smaller the value, the better the score for both of these. BIC puts a larger penalty for model complexity than AIC does, but otherwise they're very similar calculations. All right, so now the visualizations that we want to use, that I strongly recommend that for everything you do in data science, if you can make a picture out of it for a data visualization, you should, and this is no exception. All right, so the first one I want to show you is bar plots, where we show the correct value by the predicted value. All right, so here I have my predicted value, predicted classification. 1 is edible, 0 is not edible. And then inside, we can see how frequently did my model get it right? How frequently did my model get it wrong? So when my model predicted, or when my model said it was poisonous, we can see that my model got right 82% of the time. When my model said it was edible, got right 82% of the time. Also, this was on the training set. On the test set, we got similar values, but we did a little bit better over here on the test set, but comparable. Now we're going to, basically do the same trick, but now on the horizontal axis, I'm going to have the correct value, the true value. And so on the training set, when the true value was edible, my model got right 84%. When the true value was poisonous, my model got right 79%. And so something to consider is that 21% aspect. This is the training data. Over here is the test data. The test data is a more realistic representation of what we'll see in production. And so here, the true value is poisonous, but 20% of the poisonous mushrooms were declared as edible. 20%. So like that's not really the right way we would, that's kind of high, right? Wouldn't you want to like reduce the risk? And so in real life, if I was doing edible and poisonous, I would, increase the criteria for saying that it's edible, which what would happen is that I would get fewer errors here, but the errors over here would grow. And so, that's something to, be mindful of on that. Now, the ROC curve, we talked about that already, where we're using the true positive rate and the false positive rate in the graph, and it will plot this out for us very nicely. And you'll notice that I use the colorized equal true to give that color bar on the right-hand side. Now, every single one of those statistics that I showed you a moment ago in that long vector, character string vector, can be dropped into the measure and the x dot measure parameters. So any two in that list can be put into here to generate a graph depending on what is of significant interest to your project. By far, the ROC curve, the receiver operating characteristic curve, is by far the most common one to look at, but the other ones are interesting. And so that one was training. This one is test. Now, another one that I've used in the past professionally that has gone over well is to use what I call a bubble plot. And so in a bubble plot, this is actually just a scatter plot, but I changed the size of the dot to correspond to the frequency. And so you'll notice that I've got all the situations for the target variable value and the predicted class. And this is really just a representation of that confusion matrix we looked at earlier. And so we can see that overall how things are going in our training set and our test set. Now, something that's different from those bar plots, remember, if you look at the bar plots, you'll notice that bars percentages added up to 100%. Here, it's in the entire panel. So I have to add up 44 plus 38 plus 10 plus 8 equals 100 after considering rounding. And so I have my training and my test. If I see a big difference between my trained statistics and my test statistics, that's a sign that I have a problem with overfitting. So, it's always important to look at both at the same time to detect that as a problem. And now another one that I like to use is box plots of the modeled probabilities. And so what I'm doing here is I've got the true value here. I've got edible and poisonous, training set, test set. And I'm taking the modeled probabilities from my logistic regression model, and I'm taking those here, and those are on the vertical axis. And so what's going on here is that we can see that, the vast majority of times, about 75% of the time when it was edible on the training data, it declared, let's say, 0.72 or higher probability of being edible. When it was poisonous on the training data, it gave, about 75% of the time, my model said it was poisonous, or it gave a model probability of 0.5 or lower. Now the tails here we can see that 25%, approximately 25% of the box plot values are in this tail. 25% of the box plot values are in this tail and this outlier here. And so, like, this overlap is where what we would ideally see, the best box plot possible, is that there would be no overlap between the box and whiskers. Ideally, we would see no overlap whatsoever. Here we have some. Maybe if I improve the model, maybe if I get better data, maybe if I change the model structure, I might be able to improve it. We do have outliers. These outliers, what I would like to do is figure out what are they. And so I know that it's truly an edible value, or an edible mushroom, and it has a very low modeled probability of being edible. And so to go back and check my data, check to see if I missed something when I was filtering data, or maybe I made a mistake in handling a data point, this is what I want to look up. I want to look up this one that's also edible. edible. And here, relatively low probability, considering it is truly an edible mushroom. Maybe there was a mistake when they were recording the data. Maybe maybe it was coded wrong. Maybe it should just be thrown out. I have options. All right, so I hope this has helped you. I hope this is exciting, to let you know how to evaluate your models, give you different tools, different ways. For your homework assignment, you're going to take the data that you've already done data prep on, you're going to build a logistic regression model, and then you're going to check these statistics on it, training and test values, and I want you to do an ROC curve bar plots. I want you to visually understand your model better. And so this will be important, those visualizations, when you go to talk to your stakeholders and talk to your boss, you're going to put those bar plots in front of them. I probably wouldn't show the box plots. It's hard to explain those to people that aren't comfortable with math. But bar plots, almost everybody will accept bar plots. The bubble plots, almost everybody will accept bubble plots. The bubble plots I've had a lot of success with. All right, well, that's all I've got for you. Life is short. Do math.